Ionic compounds are very common. They occur in the Earth's crust as minerals. They're present in the foods that we eat. They are generally very stable because there are these strong ionic bonds between the ions in the lattice. Here's some examples of ionic compounds that you might eat. Here's Morton's light salt. That's a mixture of sodium chloride and potassium chloride. Both of those are ionic compounds. Tums, if you have acid reflux or heartburn, sorry. I'm sorry, heartache is just not going to help if you broke up with someone. Tums is calcium carbonate. That's an ionic compound. Calcium and carbonate. Carbonate is a polyatomic ion. Here's some pictures of minerals that occur in the Earth's crust. Calcite is also calcium carbonate. And this is trona, which is a crystalline form of this messy-looking thing here. We need to learn how to write the formulas for ionic compounds. So the metal always comes first. We write the symbol for the metal cation, and we kind of need to do some little notes to ourselves first before we write the whole formula. So first we're going to write the symbol for the metal cation with its charge. The charge is really important. And then we're going to follow that with the symbol for the nonmetal with its charge. Because it's the charges that are going to tell us what the ratio is. Why is sodium chloride NaCl instead of NaCl2? Because the charges are +1 or -1, and the ratio that combines is 1:1. So after we have our symbols with their charges, we're going to put subscripts on each cation and anion to balance the overall charge. And then we're going to double check that we did it correctly and that the charges are going to add up to 0. We'll get to some practice ones there. Ionic compounds always have a positive and a negative ion. Otherwise, they're not going to stick together because like charges repel each other. And so if you had all negative ions, they're just going to fly apart. You need positives and negatives to attract. The first element is usually a metal. Metals are the ones that form positive ions. There are some exceptions. The one that we're going to run into the most in Chem 1A is ammonium. This is a polyatomic ion that has a +1 charge. Most polyatomic ions are negatively charged, but this is an exception. So it's the metal and then generally the nonmetals. And in a formula, the sum of the charges of the positive ions has to equal the sum of the charges of the negative ions, because overall it's going to have 0 charge. And we're always going to look for the smallest whole number ratio of ions. We're not going to describe sodium chloride as Na2Cl2 or Na50Cl50, even though that is the same ratio as 1:1. They've decided that we're just going to always use the lowest ratio. That way we always end up with the same formula. Question?
How come ammonium is an ionic compound? Is it 2 gases, 2 nonmetals combined?
That's a good question. Why isn't this an ionic? Why is this an ion and not a molecular compound? Well, there's a very similar molecular compound called ammonia, which is NH3 and has no charge. So this is a molecular compound. This is an ion, a polyatomic ion. And as to why it does that, that gets a little complicated. If it has a charge on it, it's not a compound, it's an ion. And the ion, a polyatomic ion, or compounds can form from things like we saw with the hydrogen and the oxygen. When you covalently bond them together or make ionic bonds, then their properties can change drastically. So let's write some formulas. So write the formula for the ionic compound that forms between potassium and sulfur. So first we need to know what the formula for the potassium ion is. So what's the symbol for potassium? K. And we can predict from the periodic table what the charge on the potassium ion will be. +1 because it's in group 1, and the group 1 metals form +1 ions. And then sulfur. Sulfur is S. And what's the charge going to be? -2. So we write 2 minus. I wrote 2 minus. There it is. I don't know. So looking at the periodic table, if you want to do the counting backwards method, argon would be 0, and then you count back, you count -2 squares, and so sulfur has a -2 charge. Now, how you figure out how to put these two together so their charges add up to 0 is kind of a matter of personal preference. Some of you can look at that and say, oh, well, it's got to be K2S. Great. You're fine. I'm not talking to you anymore. For the rest of you, there are two different ways. I'm going to show you the understanding way first. So let's just look at these guys and figure out, well, how many positive charges and how many negative charges. So this is +1, so I've got +1 positive charge, and here I've got -2 negative charge, and then I have to ask myself, are these equal? Are they going to add up to 0? No, they're not. I can't change the charges. All I can do is add more ions. Well, I don't want any more negative ions because I already have too much negative charge. But if I had another K+, then my total positive would be +2. And so now if I have 2 K pluses and 1 S2 minus, overall their charge is going to be 0. And that's the lowest ratio. And so then I would write this formula as K2S. In the formula for the compound, you do not write the charges. No charges in the formula. Any questions about that? So let's look at it a different way. So this is the favorite method for many students, and it works most of the time. It doesn't work all the time. It's called crisscross. So you look at your charges, and if the charges are not the same, then you can crisscross. If they're the same, you don't need to. It's going to be 1-to-1. But I'm going to take this unwritten 1, and that's going to be the subscript for the sulfur. And this 2 is going to be the subscript for the potassium. And I'm going to end up with K2S.
When would that not work?
When would that not work? That's an awesome question. How about this? Let's do SN4 plus and O2 minus. Now, if I do crisscross, what am I going to end up with?
SN2O4.
I'm going to get SN2O4. Is that the lowest ratio? No. The lowest ratio is SNO2.
So can we do it that way?
You can do it that way as long as you look at the result and simplify it if it's not the smallest ratio. How about aluminum and nitrogen? Well, what's the charge on an aluminum ion? 3 plus, because it's in group 3A of the periodic table. How about nitrogen? 3 minus. So here we have charges that are the same. We don't need to do anything. We just have one of each, and their charges add up to 0, and we're like, yay, this is easy. So ALN. Question?
I was going to say, why is it negative?
Why is it -3?
Yeah.
Because it's in group 5 of the periodic table. The group,
Take 3 electrons.
Okay.
yeah, the group 5.
Okay, I remember now.
Yeah.
It goes backwards.
So, we can do the counting backwards method or group number -8. Really what it is nitrogen has 7 electrons, and the closest noble gas is neon with 10 electrons, and nitrogen wants to have the same number of electrons as the nearest noble gas. So I think of the noble gases as being like the in crowd in high school, and the electrons, I said, are kind of like your clothing, right? And so these kids that aren't in the in crowd, like nitrogen, he wants to be, and so he's going to wear the same clothes as neon, so he kind of looks like neon from the outside. Does he become neon when he does that? No, but he feels better about himself. So, whatever. I remember when my oldest son was in high school and I'd drop him off at school, and every single boy was wearing a Hollister hoodie. It was just like, oh yeah, you're expressing your individuality, all right. All wearing the same thing. But that's how we are. Any other questions? There are worse trends than Hollister hoodies. So that's writing formulas for ionic compounds. Compounds also have names. Some compounds have common names, but all of them have systematic names. And to systematically name this enormous variety of compounds, we have to give different sets of rules for different types of compounds. So ionic compounds have one set of rules for naming, and molecular compounds have a different set. So ionic compounds are generally composed of metals and nonmetals. There's always going to be a cation and an anion. And so the first thing we have to do is identify that it's an ionic compound. So we're looking for the metal-nonmetal, or that one exception with the ammonium. So if we look at these examples here, all of these have a metal first and then the nonmetal. So I think of metals as being masculine, and so it's like Mr. and Mrs. Right? If you're addressing a formal wedding invitation or something, you're going to write Mr. and Mrs. so-and-so. Why? Because that's how we do it, right? That's how everybody does it. I don't think there's any better reason than that. It's just because we kind of, as a society, we've just always done it that way. We always write the metal first and then the nonmetal, the cation and then the anion for the same reason. It's just custom. And when it's all nice and uniform that way, it's easier to recognize. It has nothing to do with the value of men and women or anything like that, okay? We can group ionic compounds into two different categories. I think this is a little bit silly, but it's in the book, so we'll go through it. One type is where the metal only forms one type of ion. And that's the metals we've been talking about so far, the ones in group 1A, 2A, and 3A. Every single time, sodium is a +1 ion. Every single time, aluminum is a +3 ion. There's no other ion that aluminum forms. That's not true of the transition elements in some of the other metals. They can form more than one type of ion, and so that's in this other category. Ionic compounds where the metal forms more than one type of ion. So these are the ones that always have the same charge. Here we've got group 1A, group 2A, aluminum in group 3A, and then we've got these guys. Scandium, yeah, we're not going to run into scandium very much. Zinc and silver are important. So we've got group 1A, 2A, 3A, zinc and silver. That's one category of metal ion. Zinc always forms a +2 ion. Silver always forms a +1 ion. Except for some really rare things we're not going to run into. So that's the small print down there. When we name these ions, the ion name is the same as the element name. So lithium ion is Li+. Magnesium ion is Mg2+. There's nothing else that needs to be added. We don't need to indicate what the charge is because we know what the charge is from the periodic table, and we've memorized zinc and silver. Then there's the others. This is a partial list of elements that form more than one compound. So let's talk about iron. We're familiar with iron. Iron forms two different ions, +2 and +3. And that's not immediately obvious from the periodic table. We saw that group 1 forms a +1 ion. Those sorts of patterns don't work with these ions. So if we have two different ions, we have to have unique names for them. And so the Fe2 plus ion is called iron 2. We indicate the charge with a Roman numeral following the element name. So we've got iron 2 and iron 3. There's an older system using the suffixes us and ic. So ferric would be the Fe3 plus, and here they've reverted to the Latin names, and ferrous would be the smaller number. You should be aware that those exist. They might show up in a worksheet or somewhere, and you can just look them up and see what they are. I won't give those to you on an exam. I personally have a hard time remembering which is which, and so I really don't expect you to remember that. If we need to know it, we can look it up. So any of the elements, the metals that are not group 1A, 2A, 3A, zinc or silver, are going to need a Roman numeral for their ion name. Okay? So, Mrs. K's tricks. So how do you remember the zinc-silver thing? Well, here we have aluminum. Aluminum's in group 3A. It forms a +3 ion. And I imagine this as being like stair steps or a ramp going down. We've got 3, we've got 2, and we've got 1. There's this triangle in here. The book didn't mention gallium, indium, or cadmium. Those are pretty unusual metals. We're not going to run into them very much. They also typically only form one charge. And so these guys will be +3, these will be +2, and this will be +1. You just need to remember those. So groups 1A, 2A, charge equals the group number. And then we've got that triangle, and anything else needs a Roman numeral in its name. And I'll be saying groups 1A, 2A, 3A, zinc, and silver so many times today that you'll probably remember it. So those were the cations. What about the anions? Because when we name an ionic compound, we give the name of the cation first, like the guy's name first, and then we give the name of the anion, like the girl's name. So monoatomic anions, single atom, we just change the element ending, the ending of the element name to "ide." So fluorine becomes fluoride. Chlorine becomes chloride. Oxygen becomes oxide. Nitrogen becomes nitride. So we're just changing the end. And this kind of goes along with my analogy of guys and girls, because when a man and a woman get married, who's more likely to change their last name? The woman. So the woman changes the ending of her name. The nonmetal changes the ending of its name when it becomes part of a compound. So your book talks about binary ionic compound, binary meaning 2. So here we have just 2 different elements. We have a cation that's going to be the metal, and we have an anion that's going to be a nonmetal. And to name them, you name the cation, and you leave a little space, and then you name the anion. So KCl. To name this, we identify what the cation is. It's potassium. We look at it on the periodic table. We see that it's in group 1A. Doesn't need a Roman numeral, and so the name of the K plus is just potassium. Cl is chlorine. This is a monatomic ion. We just changed the ending of chlorine's name to "ide," and this is potassium chloride. CaO, we've got 2 elements here. We've got calcium and we've got oxygen. Calcium, we have to ask ourselves, is this going to need a Roman numeral? Is calcium in groups 1A, 2A, 3A, zinc, or silver? Yeah, it's in group 2A. Doesn't need a Roman numeral. We don't want to write extra junk in here. And then oxygen changes the ending of its name to oxide, and we have calcium oxide. Any questions? Yes?
What happens if you have a... Oh, you just put it on.
Yeah, I think that's coming up. But what if you had something else? Like, what if you had... I'm blanking. What if you had this? SNO. Snow. Well, SN is tin. Is tin in groups 1A, 2A, 3A, zinc, or silver? No. It needs a Roman numeral. And then oxygen becomes oxide. And then we have to figure out what the charge on the tin is. That's why I haven't done examples of this yet. We've got one tin and one oxygen. And what's the charge on the oxide ion? 2 minus. If there's one of each, the tin must be plus 2. And so its name would be tin 2 oxide. We'll get to that. Any questions? Let's practice these. This is that first group where the metal forms only one type of cation. So name this compound, Ag3N. There's a cation and there's an anion. What's the name of Ag? Silver. Is that in groups 1A, 2A, 3A, zinc, or silver?
Yes.
Yeah, it's silver. Doesn't need a Roman numeral. What about N?
Needs a
Nitride. So N stands for nitrogen, and we're going to change the ending of the name. It's nitride. You don't often see women with Roman numerals, Jane Smith the Fourth. This doesn't work out that way too much. We should maybe change that. I don't know. But what we see here is similar. We'll sometimes see Roman numerals for the metals, but never Roman numerals for the nonmetals. And then write the formula for rubidium sulfide. Writing the formula, we're just going to take and we're going to write the symbols for the ions with their charges, and then figure out how to put them together. So rubidium is the symbol what?
RB.
RB. And what group is it in? 1A. So it's plus 1 charge. Sulfide means which element? Sulfur. And what's the charge on sulfur? 2 minus as an ion. So how do we put those two together? We can crisscross, and we get Rb2s. So this becomes that subscript. The unwritten 1 becomes an unwritten 1 over there. That's the formula for rubidium sulfide. Any questions?